Hey guys, welcome back. Today we're going to talk about the periodic table of elements and how it is organized. So, just a quick reminder that the periodic table is the essence of everything. Um, there is nothing around you right now that isn't built off of the elements that are listed here. And so these are essentially the building blocks for life and everything not alive as well. So it's important to understand this periodic table and understand how it's organized. So we're going to talk about that today. So the elements are arranged on the periodic table by increasing atomic number, not by atomic mass. There are some examples where the atomic mass is actually lower than the subsequent element. So, atomic number is how it increases. Atomic number is the number of protons in the nucleus of an atom. So it goes hydrogen is 1, helium is 2, so on and so forth. The atomic number is the fingerprint of the element. All carbon atoms have 6 protons. So you can't have a carbon atom that doesn't have 6 protons, just like you can't have a hydrogen atom that doesn't have 1 proton. There are some elements that have been named for people. We have ES, Einsteinium for Albert Einstein. We have CM, Curium for Marie Curie. We have FM for Fermium for Enrico Fermi. Some elements have been named for places. We have AM for Americurium for America. We have FR for Francium for France. And BK, Berkelium for Berkeley, UCal. And RE, Rhenium for the Rhine River. Some elements have been named for celestial objects. We have HG, Mercury for the first planet. We have NP, Neptunium for the 8th planet. And some have been named for characteristics of the element, like chlorine from the Greek chloros, meaning like a greenish yellow color. For many elements, the symbol matches its Latin or Greek name. Hg, Latin name, hydrargyrum, means liquid silver. So Mercury literally looks like liquid silver. Mercury is actually also the only element on the periodic table for metals that's a liquid. All the other metals are solids. It was later named after the Roman god Mercury, speed and nobility. W is tungsten, and tungsten symbol comes from wolfram, the ore in which it is found. So that's why it starts with a W, is because wolfram is the ore, and that starts with a W. The periodic table is arranged in such a way that chemical and physical properties display repeating patterns. This is called periodicity. Metallic elements are on the left side of the periodic table, and non-metallic elements are on the right side. So your metals on the left, your non-metals on the right, and in the middle you have your metalloids. Metalloids, kind of like an alienoid, it has characteristics of both metals and of nonmetals. So on your reference table, on the first page, you'll see Table A. And on Table A, it says standard temperature and pressure. So every element on the periodic table is considered in terms of STP, standard temperature and pressure. And these temperatures and pressures include 0 degrees Celsius or 273 Kelvin. And standard pressure is 1 atmosphere or 101.3 kilopascals, which are both listed on your reference table. So based on this temperature and this pressure, at STP, standard temperature and pressure, mercury is considered to be a liquid, and bromine, nonmetal, is considered to also be a liquid. Also on the periodic table at STP, the gases, these are all nonmetals. So nitrogen N2, oxygen O2, fluorine F2, chlorine Cl2, hydrogen H2, and all the noble gases, they are gases. So again, it can change phases. It can be a liquid or a solid at different temperatures and pressures, but at standard temperature and pressure, which again is these based on your reference table, that is the form in which they are. Properties of metallic elements. So when you think of metals, what do you think of? Generally, they are solid. So that's, again, at standard temperature and pressure. So at 0 degrees Celsius, you might think that's kind of cold to be standard temperature, but 0 degrees Celsius is freezing. But it's still metals are solids at that temperature, except for mercury. They're also great conductors of heat. I can attest to that because tonight I cooked with my cast iron, and the whole cast iron was very hot, which is why I used a mitten to move it instead of holding the handle with my hand. They're great conductors of electricity, which is why all your wires are made usually with copper. They're usually shiny. They're ductile, meaning they can be put into wires. They're malleable, you can shape them. And they can be soft or hard. There's actually some very soft metals, like I will show you at some point sodium. Sodium is a super soft metal. But then you can and I can physically myself cut sodium. And in comparison, if you think of other metals, even like aluminum's very soft. But steel, which is a mixture of several metals, steel is super hard, right? You have steel to hold up bridges and buildings. They have high melting points, and the metals will always lose electrons. They never want to gain electrons because it's easier for them to lose a few than to gain a whole bunch to get to the valence electron number that they want. Metals will lose electrons and go from a neutral atom to a positively charged ion called a cation. So again, all elements start off as neutral on the periodic table. They're neutral because they have the same numbers of protons as they have electrons. It's only when the metals lose some electrons that they have more protons than electrons, and then they become positive because of that. So here you have a neutral sodium atom just based off the periodic table. And when it loses an electron, it will then have more protons in its nucleus than electrons, so it will have a +1 charge. And this is showing that it lost 1 electron, so it's off of the sodium atom. Similarly, you could have magnesium, which is in group 2, and it goes from neutral as it's shown on the periodic table, and because it has 2 valence electrons, it wants to lose both of them, and so it will go to +2 charge, and here's the 2 electrons off of the magnesium atom. Properties of nonmetallic elements. So nonmetals are poor conductors of heat, like around your wire or around your pan, you would have usually like on the handle part, some sort of like plastic coating. That's poor conductor of heat because you don't want it to burn your hand. So it's not going to transfer heat well into your hand. They are not conductors of electricity, which is why wires are coated with some sort of plastic also. They are not shiny. Their solids are brittle, meaning they can break easily. They're generally low melting points. You can melt them pretty easily. It's easier to melt plastic than it is to melt cast iron pan. They generally have low boiling points, so it's also easier to boil plastic than it is to boil your cast iron pan. Can you imagine boiling your cast iron pan? That would be crazy. Non-metallic elements tend to gain electrons to become negative ions called anions. And non-metals, they like to gain electrons because, again, they're closer to having the magical number 8, the number of valence electrons they want, so it's easier for them to gain a few than to lose all their valence electrons. Non-metallic elements tend to gain electrons, become negative ions called anions. Here are some examples. So fluorine goes from neutral. Again, all elements, as is on the periodic table, start off as neutral. So when it gains an electron, then it's going to have a -1 charge because it goes from neutral, having the same number of electrons and protons, to having one more negative electron. So now it's a negative charge. Similar to sulfur, starts off as neutral, as they always do, and then when it gains 2 electrons, it will have a -2 charge. Phosphorus starts off neutral, it wants 3 electrons, so when it gains those 3 electrons, it will turn into phosphorus with a -3 charge. All right, so we covered our metals, our nonmetals. Let's talk about the metalloids, the ones in the middle, right on the staircase, the zigzag. They are solids. They can be shiny or dull. They are ductile and malleable, and they conduct heat and electricity better than nonmetals, but not as well as metals. So I would expect these characteristics because they have some properties of being metals and some properties of being nonmetals. That's why they're semi-metals. So it makes sense that they're a solid, and they could either be shiny or dull because, again, they could be a little metallic looking or a little bit not. They have some properties that metals have, ductile and malleable. And they do conduct electricity and heat, but they only do it better than nonmetals who don't do it at all. They don't do it as well as metals who are very good at this. So their properties make sense. Okay, let's talk about the Brinkelhoff twinsies. So on your reference table, your nonmetals side has bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And these guys all like to bond to themselves. They're called the Brinkelhoff twins because in real life, you'll never see oxygen by itself, not bonded to another oxygen atom. And similarly, you'll never see nitrogen not bonded to itself. It's always going to be nitrogen bonded to another nitrogen atom. So these are the Brinkelhoff twins. And they're diatomic molecules because there are 2, di meaning 2, atoms bonded together in a molecule. So here you can see them. Here's 2 hydrogen atoms bonded together, 2 nitrogen atoms bonded together, oxygen, fluorine, chlorine, bromine, and iodine. So in the future, when I refer to oxygen or chlorine or something, you can always just assume I'm talking about 2 atoms bonded together. It's not just a single oxygen atom because you can't find that naturally on our planet. Brinkelhoff twinsies. Brinklhof. These are all like the atomic symbol letters for the elements. So your periods on your periodic table, it tells you right here, they run straight across. So here's the first period, second, and so on and so forth. The period number indicates the number of occupied principal energy levels which contain electrons. So if you look in the bottom left-hand corner of the element, you'll see like hydrogen and helium, they only have one electron shell. And then if you look in the second period at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, you'll see that there's two different electron shells. You'll have a 2 dash and then some number. So that's saying you have electrons in the first shell and electrons in the second shell around the atom. And it continues going, so once you go into the third period, there'll be 3, fourth period, there'll be 4. The vertical columns are called groups or families. So when you're going up and down, it's called a group. When you're going across, it's called a period. So these are periods. And these are your groups. Group 1 are called alkali metals. Alkali metals are so reactive that they are never found in pure form. So they just react before they can even be by themselves. They have only one valence electron. So what that means, if they only have one valence electron, is they're always trying to lose just one electron because their inner orbitals are already full. So once they lose their outer electron, they are happy. So they'll all have a +1 oxidation state, which you'll see in the top right corner of the elements. Francium is the most reactive of all the alkali metals. So you'll definitely never see francium itself because francium is the most reactive metal on the periodic table. Group 2 alkaline earth metals. They are so reactive that they are never found in pure form in nature either. They have 2 valence electrons, and so they're trying to lose both of them because their inner orbitals are stable, so they want to lose the outer 2 valence electrons. And when they lose 2 electrons, they'll have a +2 oxidation state, which means they're forming +2 cations. Alkaline earth metals are not as reactive as alkali metals, but they're still very reactive. Okay. Oh, on your reference table, you will see that there is a table based on metal reactivity, and the most reactive metals are up here, and the least reactive go down here. So like lithium, rubidium, potassium, they're all in groups 1 and 2. Groups 3 through 11 are considered to be your transition metals. Transition elements, they can form compounds by losing electrons from the 2 outer energy levels. They have several oxidation states, so depending on who they bond with, they might choose one oxidation state or another. They form really beautiful colored solutions. So transition metals are probably the prettiest on the entire periodic table. The ions of transition metals are usually colored both in aqueous solutions and as solids. Aqueous just means in water. Here are your other metals: aluminum, mercury, cadmium, bismuth. The metalloids are the metals that are, or the metalloids are metalloids that are touching the staircase right here. Your nonmetals are right after the staircase. That really includes group 17 and group 18, but we specifically have names for group 17 and group 18 also. Notice how hydrogen is highlighted even though hydrogen looks like it's on the metal side, it's actually a non-metal. It's the only one on the left side of the periodic table that kind of doesn't fully belong there. Halogens are group 17. They are nonmetals, but they're specifically called halogens. They are salt formers, and they all form ionic compounds with reactive metals. So group 17 really likes to bond with group 1 because they have 7 valence electrons, and group 1 only has 1. So they want to steal the 1 electron from the alkali metals. And when they do that, they form -1 ions. They are the most reactive nonmetals, and fluorine specifically is the most reactive. Again, you'll always find your Bringelhoff twinsies bonded to themselves. So fluorine is a Bringelhoff twinsie, and chlorine's in there too. So is bromine and iodine. They like to bond to themselves. Because of their reactivity, the halogens do not occur as free elements in nature, so they'll always be bonded to something. Last but not least, we have group 18, the noble gases. Again, they're too noble to bond with anyone on the periodic table because they have the number of valence electrons that they want to be stable. So there's no reason for them to bond with anybody. So they're called inert because they're not reactive. All are stable monatomic gases. Monatomic meaning one atom. All have a full valence outer electron shell, usually an octet, meaning it likes 8, except for helium, which only has 2. The innermost electron orbital only wants 2, so that makes sense. Krypton and xenon have been forced to react to form compounds, so you can have them react the larger ones, but generally they don't like to. And then you have the rare earth metals. They're called the lanthanide and actinide series. They really belong to period 6 and 7 respectively. They're not really rare, but are found pure, usually found mixed together in small quantities. Sorry, but are not found pure. That makes more sense. So this is what it would look like if the periodic table include the lanthanide and actinide series, but it kind of looks dumb because it's so long. So they just kind of cut that part out and put it down here. So it could just be the metals and then your metalloids and then the nonmetals. So since the periodic table has been constructed to look like this, there have been newer renditions of it. So here's one example of how they're trying to make it so that the lanthanides and actinides aren't awkwardly kind of placed in the bottom here. So they include them like this and also include the transition metals while still organizing the elements based on the number of valence electrons and atomic number. So this is one model of it. Here is another model. It's hard to imagine the periodic table looking differently than what it currently looks like, but these might make more sense for how to organize the periodic table than what we currently use.